Question comes up, how do we balance oxidation-reduction reactions? Let's look again at the net reaction of iron and copper 2 sulfate. You have iron solid plus copper 2 gives you iron 2 plus copper solid. We can write this reaction in terms of two half reactions. Half reaction is one of the two parts of an oxidation-reduction reaction. One involves the loss of electrons, which is the oxidation, and the other involves the gain of electrons, which is reduction. To write a balanced redox reaction, you must write the half reactions, balance the atoms, balance the charges, and finally balance the number of electrons transferred. So getting back to our net ionic equation here, we need to figure out what's being oxidized and what's being reduced. So the oxidation half reaction would be a case of iron solid going to iron 2 plus. The reduction half reaction will be copper 2 going to copper solid. You got iron increasing in oxidation state and copper decreasing in oxidation state. Next thing is to make sure that your atoms are balanced. This is a simple example, so yes, the atoms are already balanced, one iron, one copper, one copper. The next is to balance charges. We know that on our reactant side of our iron, we have a 0 charge, and we have a 2 plus charge on the product side. The only way that we can balance this is using electrons, which are -1 charges. So I need to add 2 electrons to the product side of my oxidation reaction. If I do that, I now have 2 minuses, 2 electrons, which is a total 0 charge. So I have 0 charges on my reactant side as well as my product side. Same thing is occurring with the copper. I have a total of a 2 plus charge on my reactant side and a 0 charge on my product side. So I'll have to add 2 electrons to my reactant side, which makes sense. For reduction, it takes on electrons to get them to be both equal to 0. They're not always equal to 0, but they must be equal to the same amount on both sides. So I add 2 electrons. Next, I need the same number of electrons being released in the oxidation as being taken on by the reduction. In this case, they're the same, so I don't have to multiply by any factor. So basically, my electrons will cancel out in this equation and pull down the rest, what gets me my reaction, which looks exactly like it was to begin with because that was already a balanced net ionic equation. So we just rebalanced it and showed you how. Notice the atoms and charges are balanced. Total of 2 plus on both sides on charge, and then we have 1 of each atom on the reactants and product side. To balance redox equations, you must know charges, oxidation numbers of the species, including the polyatomic ions. You must know what's strong and weak and what it means. You must also know the solubility rules. So here are the rules to balance a redox. Number 1, you must convert the net ionic form if the equation is in the original. You must convert to a net ionic form if the equation is originally in the molecular form. In other words, you need to get rid of the spectator ions. Second, I need to write half reactions. Third, balance the atoms using H plus, OH minus, and water as needed. If it's an acidic solution, I have H plus and water at my disposal. Typically, you put the water on the side that needs the oxygen or the hydrogen when we're dealing with acidic solution. Basic's a little bit more difficult. You have OH minus and H2O. You put water on the side that needs the hydrogen because there's a 2-to-1 ratio there. But if there's no hydrogen involved, then you put OH minus on the side that needs the oxygen in a 2-to-1 ratio. Why is that? Well, because I have 1 oxygen on each one, I'm trying to keep those hydrogens balanced since they're not the issue. So basically, you balance the oxygen with OH minus, double the OH minus, add half as many waters to the other side. You balance charges for the half reaction using electrons. Then you must balance the transferred accept number of electrons in the hold reaction by multiplying by some factor. Then you convert your equation back to the molecular form if necessary by reapplying your spectator ions. Basically, this is a process to take a very difficult equation and break it up so you can balance it and put it back together. If you have oxygen in several components, it's very difficult to balance it by inspection. Note, H plus and OH minus on the same side equals water, which means if you don't need to do water in H plus, if you have to simplify it by just adding H plus to balance it or just OH minus to balance it, that's fine. You can do that. You just have to make sure that in the end you've seen the H pluses, OH minuses together on one side. That's water. Let's look at a simple example to demonstrate this procedure. We're balancing zinc plus silver nitrate, giving zinc nitrate plus silver. Now, naturally, you can easily balance this one by inspection, but we're going to go through this process just to show you how it works. So first what we need to do is find the net ionic equation, meaning we got to get rid of the spectator ions. So looking at this, we know that zinc will come down in the total ionic. Silver nitrate is a soluble salt, so that would break up into ions. And zinc nitrate is a soluble salt, so that will also break up into ions, and silver will come down. So here's my net ionic equation. Next I get, my total ionic equation. Next I have to get my net ionic equation, which means I got to get rid of spectators. The only spectator there is nitrate, so we'll get rid of that. Now notice that I have a 2 coefficient in front of one side and 1 on the other. That doesn't matter. It's not balanced. We're going to fix that in the end. So then I bring down my rest of my components. So my net ionic equation is zinc plus silver 1 gives me zinc 2 plus silver. Next we'll need to write the half reactions. So I have my net ionic equation, and now I got to write what's being oxidized and what's being reduced. So looking at this, see that zinc is going from zinc solid to zinc 2 plus is an oxidation. I see that silver plus going to silver solid is a reduction. Next thing I've got to do is make sure my atoms and charges are balanced. Now we must balance the atoms. However, in this case, everything's already balanced. I got 1 on each. And then I got to balance the charges. The only thing I can do is add electrons, -1 charges, to balance the charge. So let's look at my total charges. Zinc solid, I have a 0 on the reactant side, and zinc 2 plus, I have a 2 plus on the product side. The only way I can fix this is by adding electrons, which are -1s. So which side am I going to add my -1s to get this to balance? Well, it's going to be on the product side, which makes sense since this is an oxidation. So I'll be adding 2 electrons, and then I end up with 0 charge on both sides. Let's look at the reduction. I got +1 on the reactant side and 0 on the product side. I will have 1 electron on the reduction side, which makes sense since reductions take on electrons. And once again, we have 0 on both at that point. So I add 2 electrons to my oxidation, giving it 0. So I have 0 on my product and 0 on my reactant side. And I add 1 electron on my reactant side of my reduction, giving 0 on both. Now note that it's not always 0. It could be +2 on both sides, etc. It just happens to be on this particular example that it went to 0. So that means I have 2 electrons on my oxidation side and 1 electron on my reduction side. Next, we need to balance the number of electrons transferred. You see I'm giving up 2 on my oxidation of the zinc, but I'm only taking on 1 from my reduction of the silver. So therefore that silver reaction is going to happen twice to get my electrons to be the same. So multiplying the silver reaction by 2 will give both half reactions 2 electrons that will cancel out. So I'll multiply it by 2 and my electrons cancel out. Bring down everything. So that gives me zinc solid plus 2 silver pluses, gives me zinc 2 plus and 2 silvers. At this point in time, my equation of atoms and charges should be balanced, and it is. You see I got 1 zinc on both sides and 2 silvers on both sides. And what about charges? Well, zinc is a 0, and I have 2 pluses from the silver, so I have a 2 plus on my reactant side, and I have 2 plus from the zinc, 0 from the silver. I have 2 plus on my product side. So therefore, it is a balanced net ionic equation. However, this was a molecular equation to begin with, so I'm going to have to put back my spectators. So I have to put back the spectators, making sure that the atoms stay balanced. Okay, if correctly done, the charges in atoms should be balanced. So I have zinc, I bring it down. Nitrate was the ion that spectator we dropped on silver, so I put that back. Got to make sure that I only have 2 silvers, so by putting in the nitrate, that didn't change my number of silvers. Zinc nitrate, I have to put that one back. Once again, I had 1 zinc. By putting the nitrate, that didn't change my overall coefficient in front of the zinc. And bring down my 2 silvers. This is my balance equation. As I said earlier, you could have done this by inspection. However, I was taking a simple example to show you the process. Now, in the test, if I tell you to do the redox, you're going to have to do the redox by balancing it by half reactions. You cannot do it by inspection. Let's look at a little bit more difficult example now. This is a net ionic example, so I'm going to have to write the half reactions. So I got iron 2 going to iron 3, and I got permanganate going to manganese 2. Notice the H+, that's an indication that this is an acidic solution, which means I have H+ and water available for me. Next step is to balance atoms. See, I have 1 iron on both sides, so I don't need to change that on the oxidation. But I do have to do some work on the reduction. Now we must balance atoms. However, in this example, the reduction half reaction will need to use the H+ and water, the acidic part, to balance the reaction. I will place the water on the side that needs the oxygen. You see that I have 4 oxygens on my reactant side and none on my product side. So I will end up putting water on the side of my product. Now, how many waters? Well, since I need 4 oxygens, that tells me that I'm going to need 4 waters. Now that I've placed the number of, now we must place the number of H pluses needed on the opposite side to balance the sides. Notice by placing water on my product side, I've put in there 8 H's that I need to balance out by placing 8 H pluses on the other side. Now you see that I have my half reaction balance. I have 8 hydrogens on both sides, I have a manganese on both sides, and I have 4 oxygens on both sides. Next, we must balance the charges by adding electrons. So for the oxidation, have 2 plus on one side, 3 plus on the other. I need to have 1 electron on my product side. For the reduction, I have 8 pluses and 1 minus, so I have 7 plus on my reactant side. And on my product side, I have 2 plus. So to balance this out, I'm going to have to add 5 electrons to my reactant side, which makes sense. Reduction should be taken on electrons. Next, we need to balance the number of electrons transferred. The oxidation is only giving up 1, but the reduction is taking on 5. So I'm going to have to make the oxidation happen 5 times. With that, finally, I have to balance the net ionic equation. Finally, the balanced net ionic equation, charges in atoms, is as follows if I bring everything down. 8 H pluses, 1 permanganate, 5 iron 2s, 1 manganese 2, 5 iron 3s, and 4 waters. If everything is done correctly, my atoms and charges should be balanced. Let's see if they are. I have 8 hydrogens, 1 manganese, 1 manganese. I have 5 irons, 5 irons. I have 4 oxygens and 4 oxygens. So my atoms are balanced. What about charges? I have 8 pluses and 5 times 2, 10 pluses. That's 18 pluses and 1 minus. That's a total of 17 pluses. On the other side, I have 2 pluses and 5 pluses. That's 17 pluses. So I have a balanced net ionic equation. Now if I had spectators, then I would put them back on. I just started off as a net ionic equation. Notice if you did this by inspection, you would never put 5s in front of those irons, so you would never get it correct. You have to balance the charges as well as atoms to get this correct. Let's look at this one. This is a molecular equation. So we need to figure out the net ionic equation first. So I need to look at things and talk about what's soluble and what's going to break up, and then look at the ions on both sides. Potassium permanganate, that's a soluble salt. Well, how is potassium on the other side? It's part of KCl, which is a soluble salt. So that's a spectator, so I can get rid of that potassium. Permanganate, okay, manganese on the other side is part of this soluble salt here. So that's going to break up. So I got permanganate going to manganese 2. So I can bring that down. Let's look at the next one. Sodium nitrite. Well, sodium is going to be as an ion on this side, and sodium nitrate is going to be an ion as well. That's a spectator, so I can get rid of the sodium. However, the NO2 minus going to NO3 minus, that's not a spectator, so I can bring those down. Then you have HCl. Well, that's a strong acid. H plus going to H2O, that's chemistry, so that's going to come down. However, though, the chloride is a spectator in all cases. So I bring down my H plus and my water. So there's my net ionic equation. Notice that I have to remove the spectator, that KCl is not part of the net. We must remember to put it back at the end, otherwise it won't balance. So I need to remember to put that back on at the end of the reaction. So now we're going to figure out what's oxidized and what's reduced. We see that NO2 minus is going to NO3 minus. That's an oxidation. MnO4 minus is going to Mn2 plus. That's a reduction. Next step is to balance atoms. We see that I have 1 nitrogen on both sides. So that's balanced, but now I got to balance oxygens. This is an acidic solution because of the H plus. So then I have H plus and H2O at my disposal. Since I'm 1 oxygen away, that means I'm going to add water to my reactant side. So now I got my oxygens balanced, but now I have a 2 hydrogen problem, so now I'll add 2 H pluses to the other side. As for the reduction, we've got 1 manganese, 1 manganese. I got 4 oxygens, so therefore I would add 4 waters. And then I have to fix my hydrogens, which is 8 H pluses. Next, I got to balance charges. Over here, I got a total of a -1. Over here, I got a total of a +1. So to balance this out, the only thing I can have is -1s. So I'm going to have to add 2 electrons to get this to equal. If I add just 1, it gets to 0, and I'm going to add a second one to get it to balance out. So I'm adding 2 electrons to equal -1 and balance it out on both sides. Over here I have a total of a +7. Over here I have a 2+. So to balance this out, I'm going to need 5 electrons on my reactant side. If I add 5 electrons plus my 7, that gives me a 2 plus and a 2 plus. Next step is to make sure I've got the same number of electrons being released as it being used. So I'm going to end up multiplying the oxidation by 5 and taking the reduction and multiply that by 2. So what happens there is my electrons, 10 of them, will cancel. And then I will bring down everything from my balance equation. Get 2 permanganates, 5 nitrites, 16 H pluses, 5 waters, 2 manganese 2, 8 waters, 5 nitrates, and 10 H pluses. Now here I got to make sure that everything is balanced, meaning if I have anything in common or any number that's divisible through all of them, I got to give it to lowest terms. You can see here that the equation can be reduced since it has some common species on both sides. I have 16 H pluses and 10 H pluses. That's like saying I have 6 H pluses. I have 5 waters and 8 waters. That's the same thing as really having 3 waters on this side. The other ones cancel. So I bring that down. So this is my balanced net ionic equation. So at this point, all my atoms and charges should be balanced. Let's check it out. I have 2 Mns and 2 Mns, manganeses, so that's balanced. I have 5 nitrogens, 6 hydrogens, 6 hydrogens. I got 8 oxygens plus 10 oxygens, that's 18 oxygens. We've got 3 oxygens, and 5 times 3, 15, 18 oxygens. So the atoms are balanced. What about charges? 2 minuses and 5 minuses, that's 7 minuses, and 6 pluses. That's a total of a 1 minus. I have 2 2s, that's 4 pluses, and 5 minuses, that's a total of 1 minus. So my charges and my atoms are balanced. This is the balanced net ionic equation. But I have to go one step further because this is a molecular equation, so I got to put the spectators back on. Last we put back the spectators, making sure to keep the atoms balanced. So for the permanganate, I had potassium, so I put that back together. For the nitrite, I had sodium nitrite, I put that back together. For the H+, I had hydrochloric acid, manganese 2, water, and sodium for my nitrate. However, this is not a balanced equation. It's still missing something. Note we must add back the potassium chloride that we took out for the entire reaction to be balanced. So I'll bring down my KCl, but how do I decide how many potassiums? Well, if you go back and look, this is the only way I can balance potassium is to put back that KCl because it's nowhere else to be found. So if I add 2 Ks, that means I'm going to have to put 2 potassium chlorides. Now that should balance my chlorines now as well. 2 chlorines and 4 chlorines, that's 6 chlorines and 6 chlorines. So I needed that to balance my chlorines as well. So you can check the equation at the end and everything should be balanced, atoms as well as charges. Here's one that we're looking at that starts off with a net ionic, but it's a basic one. It has OH minus. So we need to figure out what's being oxidized and what's being reduced. We see that CrI3 is going to CrO4 minus and IO4 minus. Note that chromium is going from a 3 plus to a 6 plus, and iodine is going from a 1 minus to a 7 plus. So basically, both species are being oxidized in the same reaction. And what's being reduced? We got Cl2 going to Cl minus. It's going from a 0 charge to a -1 charge. Next thing we had to do is balance how atoms, we see that I got 1 chlorine and 1 chlorine, not a problem. I got 3 iodides, 3 iodines, and 1 I, so I need to multiply that by 3. Next, I got to look at my oxygens. I got 3 and 4, that's 12 oxygens, and 4, that's 16 oxygens that I got to balance. I don't have any on the other side. Since this is basic, I know I got OH minus and water. Now I should go ahead and say, okay, I need to put 16 OH minuses on this side. Well, if I do that, I'm going to add water to the other side. I'm going to have to add 8 waters to get my hydrogens balanced, but notice that I'm adding 8 more oxygens. So now that goes to 24. So I'm going to go back and forth several times until I get to the final answer. Since I know I'm going to do this, I know that I need to balance oxygen, and I don't want to mess up the hydrogen. So I will double the amount of OH I need on the side that needs oxygen. I need 16, so I'm going to put 32. And put half as many waters. This will keep the 2-to-1 ratio and keep everything balanced. So I had 32 OH minuses and 16 waters to the other side. Now all my atoms are balanced. Now for the reduction, I need to just put a 2 in front of the chlorine. Next we're going to do charges. We got 32 minuses on our reactant side, and we have 2 minus and 3 minus, 5 minuses on my product side. So I got 32 minuses and 5 minuses. The only way to balance this is to add 27 electrons to my product side. For the reduction, I have 2 minuses, means I'm going to add 2 electrons on my reactant side. Now I need the number of electrons to balance, so I'm going to do 2 times 27 for the oxidation and 27 times the 2 on the reduction. Then bring down everything. So I need to reduce this if I can, and since I got odd and even numbers, that's not going to be able to reduce, but all my atoms should be balanced as well as my charges. Let's check it out. I got 2 chromiums and 2 chromiums, 54 chlorines, 54 chlorines, 64 hydrogen, 64 hydrogen, 64 oxygen. I got 8 and 24, that's 32, and 32 is 64 oxygen. Charges, 64 minuses, and I have 2 times 2, that's 4 minuses, and 6 minuses, that's 10 minuses, and 54 minuses is 64 minuses. So this has all atoms and charges balanced. Homework 33. Notice on my website there's a whole bunch of redox equations that I've done in 134 lab. You can go there and get some other examples if you want to work some more problems. It'd be under the 134 lab. You click on it, go to there on my website, and there is about 24 of these type of problems.